Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's Ichikara pack puzzle. Um, I love doing these, so I will keep posting these, but they're not very popular, so not everybody loves watching these. But I'm just gonna keep posting them because I just enjoy doing them. Anyways, we have Lava Cake here. We also have Snowflake Ichikara, and we have Bridge, all by Michael Lefkowitz. And they should be fairly easy, so you should be able to do them all sort of in one go. Anyways, let's get to the rules. We have Ichikara, which we need to divide the grid into regions. So every cell in the grid must be part of a region, and a region contains the numbers from 1 to n once each, where n is the largest number in the region. And a question mark can stand for any number. In addition, we have regions also for snowflake and for bridge. We have regions may also contain empty cells here. So a valid region could be something like this, because you have the digits 4 through 1 once each, so that would be a valid region. But part of the problem here is this would not be a valid region because the regions have to be orthogonally connected to each other, which means you can go from any cell in the region to any other cell in the region just by going through edges, all while staying within the region. But obviously this is blocked off from any other cell by this. So this is not a valid potential solve, right? Because this 2 doesn't have a 1 to be a region part of. So it cannot, this is not actually valid as a region. But those are examples of how you can solve these Ichikara puzzles. Anyways, those are all the rules. If you like to play along, I'm going to post links to each of the puzzles in the description. And now I'm going to get started. Let's go. Okay, one thing I like doing in Ichikara puzzles, ooh, this is a lot, is counting up each number, each digit, and seeing how many of each digit there are. This is a lot. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 ones. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 twos. So that means, okay, because each 2 has to have a 1 that it's also part of a region with, since there are 14 ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and there are 15 twos, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15s, this question mark has to be a 1. How many 3s do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 3s. We have 4 4s and 2 5s. So we have 2 regions that are 1 through 5, 2 regions that are 1 through 4, a hell of a lot of regions that are 1 through 3. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 minus 4 4s means 8 regions that are 1 through 3. And we have 3 regions that are 1 through 2. Okay. So let's start with the 5. 5 has to have a 4 with it. It cannot be, it has to be this 4 for this 5, because if we try to go around, the problem is we have to either include the 4 or we would have duplicates in the region, which is not allowed. So this is the same region. What about this 5? This 5 could be with either of these 4s. So this is fine. This could be 3, 2, 1 here. This one has to be part of that too. Because there's no other place for it, and one is not part of a region, right? Um, because we have 15 ones, but we also have 15 twos. So every two is already taking a one with it, and it's to be part of its region. So this cannot, okay, so this is wrong thing. We know there's a boundary here, there's a boundary here, and the boundary here, because this has to be one and a two. So this must be part of a region, uh, and this is part of a region, and this must be 1 and 2. This is 1, 3. It cannot be with 1, so this must be 1, 3, and 2 here. We're going to make this yellow. So we have 1, 2, 3 here. And that is done because it cannot enter in these regions. This is part of a region, and then it's done. So we're going to make this a gray region. This one also must be part of a region, so it's 1, 2. It could be part of 3. We're not sure. This one has to be part of 2. Similarly, actually, I guess we should make this pink, and this we can make this orange. So we have blockers here. This one has to go down there. Hmm. We don't know where it's, so it could be either of these that it's part of. It could be neither of these. Okay, so this is a boundary, definitely. This one has to be part of some other one. This is a boundary. Anytime you have digits that are the same digit, they cannot be part of the same set. So this has to be 1, 3 that way. This cannot go that way then. So this is done. This has to be part of that, and it has to have 1, 3, and 2. So then this is part of its own region. And then it's done there, because there's no other place for it. This 1 and 3 have to go down. So it goes there, and then we needed access to a 2, so it can't go here, so it must go and continue here. It could be part of 5, actually. So this is blocked here, but we don't know if this is done there. 1, 3 has to be 2. It could be part of the red. So we don't know. We just know there is a boundary here. And this has to be with 1, 3, and then 2. So then we have a guaranteed boundary here. So this needs access to a 3. It could be one of these. It could be one of these. This is a separate boundary here. This is interesting. How do you disambiguate this? I don't know if you can. That's strange. Yeah, I don't know how you disambiguate this. Or if you can disambiguate it. Oh. Hold up. Did I mess this up? Maybe I messed this up. Okay, yeah, I messed that up. Okay. That's how we know. Um, this could go this way. So this has to be 1, 2, 3 here, right? If we try to go 1, 3, 2 here, the problem with that is this could be 3, 4, 5, but then you could go only 1 here or 1 here. It doesn't have access to a 2. So this cannot be 1, 3, 2, because then that would block this from being valid. So this must be part of red. So it's 1, 3, 2 that way. Which means this is a region, this is a region. This is green by itself. And this must be part of that. And this 5 doesn't have access. I guess it could be 1, 2, 3, 4. So this is all part of the same region. And we don't know where the 5 has to go. That's interesting. So this is a boundary here. So 3... Okay, this 3 cannot go through here. It needs access to a 1, so this has to be 3 and 1 by itself. And then it could be either of these 2s. We're not sure which. And then it could go to the 4. But that's it. So it goes to one of these 2s. Yeah, how many? So we have 1, 2 here, 1, 2 here, 1, 2 here. That accounts for all the 1, 2 pairs in this grid. Because again, remember, we had 12 3s, we had 15 2s. So that means, and 15 1s. So that means all the 1, 2s are accounted for. So the rest must be 1, 2, and 3. So this has to be 1, 2, 3 here, which means that's done. This has to be 1, 2, 3 here, and that's done because it cannot, it's blocked by 2 and 3 there. This must be 1, 2, 3, and that's done. So this 1 has to exit out. Ooh. That's bad. Where is that one? That can't be right. Maybe it is. No, it can't be right. Okay. This is becoming a little harder than I thought. Oh, this could be 1, 2, 3. Right. So this 3 needs access to 1 and 2, but it doesn't actually have to be part of 4. Oh, I've been making quite a bit of mistakes here. This 1 needs to access somewhere else, so this is done. This has to be 1 through 4 here, and this is exit here. So this has to go this way. And it's 1, 2, 3, 4, 5. So that's done as a region. And this 1, 3 needs access to a 2. So that's done. And then this is a region here. 1, 2, 3, 4. Okay, so every region should be set. We have 1, 2 here, 1, 2 here, 1, 2 here. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 3, 2, 1, 2, 3, and 1, 2, 3 here. This is 1 through 4, this is 1 through 4, and this is 1 through 5, and this is 1 through 5. Huh, that was actually very interesting. I made some bad assumptions there. That was, not sure how to avoid those in the future. That was interesting. Very cool. Anyways, let's get to the next puzzle, which is Snowflake. Okay, let's start by counting. That's a lot of 1s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 1s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 2s. So 14 1s and 13 2s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, 14 1s, 13 2s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 14 1s, 13 2s. 14 ones, 13 twos. How many threes? 4. There's 4 threes. How many fours? There are 4 fours. How many fives? There are 4 fives. Okay. So that means this question mark digit could be 1, 2, 3, or 6. It cannot be 4, 5 because there are only 5 fives and 4 fours. And there are 4 threes. So if you had an extra 5 or 4, you cannot have an extra 3 that would match it. So that's why you can't have 4 or 5 there. But this could be 6. So every 4 is part of a 5, and every 4 is part of a 5, and it's part of a, well, not guaranteed 3. The 4 here has to be part of this 3, because otherwise it doesn't work, and this therefore it must be part of this 2. So this is a boundary here. This 4 I think has to go through 2 and 1 to get to 5. Yes, it has to go through 2 to 1 some way. So 2, 1, it can't go through that 2. So if it tried going through that 2 and that 1, it doesn't, it's blocked. And every 5 must have a 4 as a part of it. So this 4 must get through here. Can't be 1, 2 here because then it's blocked. I think the only way is here. So this has to be this set. And then it accesses here. So then it could access 5 or this 5. This 4 has to go through here. So it has to be part of, oops, you have to have at least 3 and 2. And you have to access the 5. So it cannot be part of this 1. So it has to be through 3. Because otherwise, if it goes 4, 1, 2, it's blocked. So it has to be 4, 3, 2, 1, and then it must access the 5. And this blocks the pink from going here, so the pink has to continue here. Blue has to go here, and this is done. So this is done. These are blocked. This is a 1 by itself. This 2 needs access to a 1. So we have 2 and 1 here. This 2 needs access to a 1. So we have 2 and 1 here. So that's done. This 5 needs access to a 3. And it's going to be blocked by the 1s and 2s. Therefore, this must be 3. So this is 3, and this must be part of it. And therefore, it's blocked from the rest. So this is done this way. So this is pink. This green could only go through 1 and then 5. But if it goes this 5, then this is blocked from this 5. So this has to be part of green. This is one region. This is another region. Again, we have 14 ones. Then we have 13 twos. So we have the only singleton 1 by itself. Every 2 then must be accessing a 1. So this must be 1 and 2, right? Because the other ones have to correspond to a 2, guaranteed, because we have this as 1. So this is a 1-2 pair. So that's done. This 1 then must access the green. So this must be part of green. And so it cannot go through here. It has to go through here. And that's a region by itself. We have 1 and 2 here, and then a 1 and 2 here. So this will be gray. We can make this yellow. This 5 needs access to a 4, and this 4 needs access to a 3. So therefore, it must access this way, and it has to access this 1 because the 1s, again, have to correspond to some 2s. So then this is done as a region. And this is done, this is done. So this must be 1, 2 here, which means this is yellow, and this is gray. So we have 1, 2, 3, 4, 5 here, 1, 2 here, 1, 2 here, 1, 2 here, 1 through 5 here, 1, 2 here, 1, 2, 3 here, 1, 2 here, 1 through 5 here, 1, 2 here, 1, 2 here, 1 through 5 here, 1, 2 here, and a 1 by itself here. And that's how snowflake works. And then finally we have bridge. Okay. How many 1s do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 1s. How many 2s? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9 2s. How many 3s? 1, 2, 3, 4, 5, 6 3s. So 6 3s. 3 4s. How many 5s? 3 5s. And 3 6s. Okay. So 11, 9, 6, 3, 3, 3. We are guaranteed 3 regions at least with 1 through 6. Could be, okay, so how many question marks? We have, I think, 2. So the question marks could be 7 and 8. They cannot be 6 or 5 because we have only 3. Well, okay, that's not complete. It can't be 6. It could be 5 and 4. That is possible. So the question marks are 1 through 5 and then 7 or 8 as possibilities. So let's do 11. And we have 9, 6, 3, 3, 3. So this is 1, 2, 3, 4, 5, 7 or 8 as possibilities. Interesting. So 2 of the 6s definitely have to cross all the way across. Hmm. Can you ever have all 3 6s going all the way across? I don't know. This 5 only is accessed through 1. So, can you have... Okay, so this is 1, 2, 3, 4, 5, 7, 8. Okay, this 5 can be accessed through 1. Okay, no, it can't be accessed through 1. It definitely has to be accessed through a 2. So, if that's the case, interesting. We have 2, 2 here and 2, 2 here. Huh. So this 5 can only be accessed through 2. If it goes 1 here, it still has to go through the 2. Obviously, it doesn't go connect that way, so it can go through 2 here, it can go through 2 here, it can go through 2 here. But it has to go through one of these 2s because it can't go up here. Um, the thing is, so then to connect with this 5 and this 6, can it connect? Okay, it cannot connect to any of these 2s, obviously. So then it has to connect through 6. So assuming that these are not 4 and 5, then this 5 have to exit out somehow and then connect with the 6. Is that even possible? I think the answer to that is no, right? The least amount of digits would be 2, 3, but then it's blocked by 3 and 2. So I think this 5 can never access a 6. So therefore, we need a 5 in one of these question marks, and this is likely to be 4. Right? Because, again, how does this 5 connect with a 6? You have to get through a 2. So say we don't go through this question mark. Say it's like 7 or 8 or 1, 2, or 3. How does this connect? It can't really, right? You can get 5, 2, 3, but then it's kind of stuck, right? If we try to go 1 here, it's blocked by 2. Each of these is 2 and 3 here, and we already have 2 and 3 accounted for. Obviously, can't go through here. This is blocked this way if we try to go through 3s. So this 5 can never access a 6, which means we need a 5 in one of these question marks, which means we need a 4 in one of these question marks. So that's 4 and 5. This 5, if this was 5 here, the problem is this would also be blocked by a 2. And you have the same problem, right? How does it access the 6? It can't. So therefore, we know we have 4 4s and 4 5s and 3 6s. This can't be 5. This is 4, which makes this a 5. So this 5 by itself must connect with a 4. It must connect to a 3. This 5 has to connect to a 6 somehow. And I guess it could be 2, 1, 3. That is possible. But then this 6 doesn't have access to a 5. So this 5, if this 5 connects to this 6, that will block the 6s from this 5. So this cannot be, this 5 has to connect to here. So we'll mark them both as blue. This 6 must connect to the one here. We'll mark them both as pink. And then this 5, I guess, the problem is this can't block this way, because then again it blocks here. So this must connect to here. Okay. This 5 connects to this red, so this must be blue. If we tried going that way, pink has to go around, and then we have problems. So it can, this must be pink, this must be orange, and this must be blue. Okay. We only have 2 1s by themselves. So, this could be part of this. You need to access the blue. So you'll need to go through a 2 because it's blocked here. And it has to go through a 2 somehow. And I think you have to go through 3 and 1, right? If you try to go 3 around here, this is blocked, that's blocked. Yeah. So the blue has to go here, which means this is blocked by itself. It cannot go 1. This is blocked here. And then we have to access 3, so this is blocked. So the blue has to go through here. it must go through the 3 and then here. So one of the 2s, it has to go through here. It goes through both 3 and 1. So that's blocked. Pink. This pink cannot go that way because it's blocked by the blue. So it has to go through the 2. So this cannot go through 2, which means this has to go through the 3. So it goes through 3. It must go through 2. This has to go through a 1, so this is blocked there. So therefore it has to go this way. It's blocked from the 2s. So it's blocked that way. So this can't be 2. It's blocked from the 1s. So this can't be 1. It's blocked from the 3s. So this is done there. This is done here. This pink has to continue here. And it goes through one of the 1s. This goes 1 through here. That would have to go through 3, so it cannot go through that. It has to go through here. So it cannot connect to any of the 1s. So we have both singleton 1s. And they're both there. So this must be part of orange. This must be part of red. Okay. This 2 doesn't have access to anything else, so it must be part of orange. So this can't be 2. So this is done here. This 2 needs access to a 1, so it's 1 here. So this is orange. And this is a singleton 1, 2. This 3 needs access to 1 and 2, so it's both of these. So this is 3, 1, and 2. This blue then must go that way. So this is done. Cannot access a 3. It has to be, this is blue. And it connects to one of these. Okay. If we go here, this 2 would not have access to a 1, so this cannot be that way. It has to go there. So this is done as a region. This 3 needs access to 2 and 1, so they're both there. This red needs access to a 3. The only 3 left is here. So this is done as a region. We have 2 2s now, and they need access to a 1. So this is 1, 1, and 2. And this has to be the other 1 and 2. And this must be blue. So these are regions here. So this is all done now. We have singleton 1s. This is 1, 2, 1, 2, 1, 2. We have 1, 2, 3 here, 1, 2, 3 here. And this is 1 through 6 here, 1 through 6 here, 1 through 6 here, and this is 1 through 5. And that's how you solve bridge. And those are all the Ichikara puzzles. This took a little longer, actually. So each one of these potentially could have been by itself. I don't know. Some of these were... The snowflake was fairly easy. So that could have been, like, very easy. I don't know. These all are starting to approach easy level. I kept on making mistakes in the lava cake, so that was a problem there. But these were fairly logical. It made sense. Anyways, I hope you enjoyed these solves, and I'll see you next time on Frank Puzzles. Take care.